Hello, everybody. Hopefully you can hear me okay. Of course, as fate would have it, the hour or two before class today, which I was planning on doing certain things, we wound up having a bunch of issues. As you probably, hopefully, have received an email from me this morning saying, congratulations, you have successfully registered to the class, and you are already on SIS, and you are already on LMS, and you have all of your I's dotted and your T's crossed, as they say. So hopefully that's all set for you. If you haven't, if this is news to you and you're hearing, you haven't received an email saying that, that means we need to kind of square things away as quickly as possible, because today, September 11th, is officially the ad deadline for courses here at RPI. So to get you in the course today, we have to make sure that your paperwork is all set and done. So we had a flurry of that already this morning, a few surprises, a few people who'd been in class, or anyway, you get I'm sure you may have been part of the drill at some point. Okay. How's everybody else doing? We'll give everyone a moment, and certainly if you want to say hello, turn on your cameras, turn on your microphones, we can kind of warm up to things. Is life going okay in general here on campus? For those of you who are
Hello?
on campus. Hello. Can you hear me?
Yeah.
Oh,
What's up?
good. Okay. Oh, just things are great here.
Yeah.
Are you?
Life's going good, I guess. I'm technically taking virtual classes, but I'm like right off campus in an apartment, so we're taking walks on campus. It's pretty nice.
Okay. Relatively quiet.
Yeah, there's like nobody on campus ever. Like especially outside of classes. I'm used to seeing people walking around, but it's just like empty. So it's weird.
Uh,
But
well,
yeah.
hopefully, somewhere in the next 2 years or a year or something like that, we'll get back to normal.
Yeah. We'll see what happens.
Fingers crossed. There we go. Fingers crossed. Lots of fingers crossed. Okay. Looks like we've got a bunch of people here, and I am streaming on Twitch. So if you run into any issues with regards to the stream quality kind of kicking down, um, everyone in my intro to game programming class was so polite as to wait till the very end of class and say, yeah, we couldn't see anything because the stream quality went to hell at some point. Speak up sooner. It could be your connection in particular, or it could be that my connection here is being terrible, which would be terrible. So we'll try to attack it from a couple of different points. If it turns out that Discord just can't keep up in terms of the quality, we'll, maybe we'll use it for the voice so we can kind of be really immediate with the voice, and we'll have the video. It's a little bit weird with the latencies and things like that, but we'll put it up a couple of different ways and make sure that the recorded lectures are accessible. I've been doing some experiments with it over on MediaSite, which isn't exactly the most friendly. It takes roughly 36 hours to upload some videos, which is terrifying. I see somebody's JoJo up there. Very nice. I could learn more about JoJo. Anyway, so we're going to be talking today, once again, hopefully I'm in the right place at the right time. This is Computer Graphics again. And we're going to talk a little bit more about OpenGL and shaders specifically, to see how people sort of did with the first homework, not first homework, but the first chapters in terms of getting things up and running. Talk a little bit about, again, my expectations. I know they're a little bit odd, especially because of the online format, trying to work things out as best we can with that. And also towards the end of class, if I can remember where I put it, hold on just one second. You'll have to bear with me. Here we go. I have been putting together a sheet, and let me bring this over here so you can kind of see it. And let me switch over to some things here. All right. Here we go. All right. Sharing my desktop here. You're going to get access to this sheet. And because there's roughly 20 people in the class, what this is, you're going to see what's odd weeks and even weeks. Don't worry too much about reading all the details. You're going to get direct access to this. And What I'm going to ask each of you to do, it's going to be more or less on a first come, first served basis towards the end of class. I'm going to need you to put your RCS ID in one of the slots, and you'll notice Computer Graphics Lecture. Those times are sort of blocked out. Let's see if I can do this. This is kind of my new fun, exciting things. So you won't be able to sign up for that because you're going to be busy here in class, right? That piece of it. But here in these slots, we're basically going to have a bunch of sort of 5 this day, and so on, that you'll sign up, and that'll be your sort of check-in time. And we're going to have the odd weeks, which is starting next week, and then even weeks, which is the week after that. So it is every other week, which is a little bit, you know, it's kind of spread out. It's kind of tricky to do, but you can imagine 10 minutes with each person. It does add up. There are plenty of other spots on the non-class days. We'll say Monday and Thursday, and so on. What I'd like you to do is, in addition to signing up for one of those slots, indicate somewhere on the others, you know, it's sort of an additional time. So if there's any way we can kind of compress a lot of the meetings to doing it weekly, that would be great as well. But I also don't want to overwhelm, you know, you've got lots of stuff going on. You have other classes going on. So obviously we have these, you know, wonderful official times where we, you know, should be able to get together one way or another. So we'll fill those up first. If there is an alternate time where we can have it, then, you know, maybe we can kind of meet a little bit more often. The main thing being, of course, you know, a couple of people have asked, you know, with regards to homeworks and projects, how are they being, you know, submitted? How are they going to be graded? All that kind of stuff, which is a little bit unusual in all of this. I'm not a big fan of just, you know, filling out a bunch of stuff, compiling it, and sending it in, especially because everything's remote and online. I know a lot of people have had issues with regards to tests and all that sort of thing. So what I really want to be able to do is sort of, you know, convince you to be following along, to be doing the exercise, to be checking in on Discord, to be active that way, so that when I do have these check-ins with you, we can kind of talk to see where you're at. You can say, you know, explain basically, you know, some of these relatively simple programs, kind of what you did, where you're at, how you approach the problem, and so on. And so figure, you know, you're getting the equivalent of, you know, a 10-minute sort of informal quiz every 2 weeks, as opposed to an hour-long test or big assignment every so often. But in order to do good during those check-ins, you're just going to basically want to keep up with things. You know, as I do post topics, I expect you to be able to kind of talk about them. So if one day I might say, well, let's talk. Did you watch the video I posted about the brief history of computer graphics and games? You know, what did you find interesting in that sort of thing? So it's going to be about, you know, largely about general knowledge. We'll see how it goes. If it turns out that, you know, some of the things are going to be better off to be submitted formally, we can certainly do that. I don't want anyone freaked out, but we're, you know, going to try to keep this kind of lively and current and keep people active, as opposed to just, you know, do everything and then just turn it in and be done with it. So that's sort of the case on things. So like I said, before the end of class, I'll go ahead and I'll make this this spreadsheet available. Any questions on that? How that kind of should work? Hopefully it should be pretty straightforward, right? It does lead to some interesting things with regards to scheduling. Some people, you know, you may be having because of the way that the check-ins are, you may have had a little bit more time on one thing than somebody else had another. You know, in the end, all the material is the same for everybody. One way or another, it'll all work out. And certainly with regards to the way the projects are going to go, you know, everybody is going to be responsible for, you know, the 4 projects and so on. You know, everything will hopefully line up as we go. All right. Now, the first project technically is, you know, we can start talking. I can start talking with you about the first project next week in our check-ins. So what should the first project be? Haven't done a lot of programming yet. You kind of just familiarized yourself with Opengl. Hopefully you've probably gotten a triangle on your screen by now. So the projects are always kind of like, okay, everything you've done in class +1, you know, take it a little bit further. Try to figure out, you know, what could you do differently, stretch your goals. You know, okay, I've drawn triangles. Can I go one further? Or can you, you know, sometimes in the earlier stuff, you might be like, well, what's going on in the next chapters? don't do it literally from there, but just, take the materials and kind of grow with it. I think I mentioned someone, instead of one triangle right now, you might want to try to figure out, okay, how would you add another triangle? How would you do something more interesting with the color? And some of the stuff we'll talk about today might fuel your ability to do that as well. Your capabilities in OpenGL are going to jump sort of exponentially within the next week compared to where you are right now. We've been kind of taking very, very small steps so that hopefully people can kind of get up to speed just in the general setup first off as well, right? So let me go ahead and I think I can clear my screen. This is kind of challenging now. How do I do this? Yeah. Just drawing on all my desktop stuff. Feel free to blurt out a question while that's going on. No questions. All right. Here's what I'm going to do. Whoops, I have to switch that back to that. I'll throw this onto another screen. And I'll go ahead and I'm going to create a link. Now, I've got to copy this already, and I'm going to make a copy of it on a regular basis, so please do not grief the sign-up sheet. Sign up. If someone is already signed up for a slot that you're interested in, you can maybe add your name to it as well if it's like an absolute positively thing, and we'll kind of work things out, or you need to comment or note or whatever. But we'll work that out. I ask everyone to be, good citizens with regards to this whole thing. Be reasonable with one another. All right, where'd that go now? All right, we're going to go over to the text channel. Hopefully the text channel in general. And I'll go ahead and I will paste that link there. All right. So we can hopefully get the hang of that. Take a moment. All right. If I click on that, there we go. Okay, I'm getting the swing of this here. Okay. So we have two big topics today. Like I mentioned, it is a matter of we have sort of OpenGL and shaders, and talk more specifically about what shaders do and the two most common forms of shaders that you've now encountered a little bit, but you might have just, chances are you just sort of programmed it in and got it to work. Hopefully you've got them loading from files. That was the kind of wrap up for chapter 2, to be able to load your shaders from files. Shaders are, really going to be your building blocks. They're going to get a lot more complex, a lot more interesting. Basically the foundations of all these programmable pipelines and newer generation graphic languages more and more rely on this concept of shaders. So that's going to be important. Let's jump back. I'm going to transition back again over here. And I'm going to refer back a little bit back and forth with regards to some of the other materials that we posted last time. Started talking about, we got into the programmable pipeline of OpenGL last time a little bit, and then we backed off of that a little bit as well. But I'm going to jump back to that one for a moment. All right. So there's lots and lots of different types of shaders that are coming into the equation now. This notion. What is a shader? Why are they called shaders? It sounds like it has something to do with pulling the shades or lighting or something like that, or pixels or something, casting shade. And it's probably best to just think of them as programs, right? Shaders are the programs that run on your GPU, right? Now your GPU, your graphics processing unit, is actually lots and lots and lots, sometimes thousands, often thousands of different processing units on your graphics program, your graphics processor in general, right? There's all sorts of sort of specialized hardware, tiny little programs that are running, and they are running these shader programs. So just like when we're developing a normal C++ program, we go through the step of, we write the program, we compile it, so the program gets compiled, then it gets linked, and then it's linked with the libraries. A lot of people have been dealing with linking things to libraries, and then it becomes a program, and then you can execute a program. It's the same thing with shaders, right? There's a little bit more specificity in the types of things that get run. You could sort of think of them as being your desktop applications versus your system applications, or maybe like that. But there are some different types of shaders that get a little bit more specific one way or the other, but they are ultimately, they're programs, right? we have this pipeline because generally the way that these programs work together is that one will have sort of a specific thing that it does that then enables more processing or enables different types of processing down this pipe, and they will hand off different types of data from stage to stage to stage as they travel through that pipeline, right? Now, so far you've seen that you had hopefully you've seen what's called a vertex shader and a fragment shader. Those are the two main types of shaders that you have to master right away. Those are the the most historical, traditional shaders. They've been in OpenGL and other graphics programming for the longest, but then a lot of new ones as well, and we'll kind of put off those other ones for a while now. We're going to keep those. So we have this idea of vertices, and then we have fragments. Fragment shaders are often, or had often been referred to also as pixel shaders, right? So on the one hand, you had these vertices, vertex shaders, that were sort of the corners of the geometry that you'd be working with, kind of a larger scale, bigger picture with regards to the types of stuff you wanted to show, your 3D models. They're all made up of vertexes somehow. We'll get into that in just a second. But then ultimately things are drawn on a screen, and in order to do that, remember we talked about the screen buffer and paint programs and so on, and ultimately things are presented to the user as points that are pixels, right, on the screen. They have an individual pixel that has to be a certain color, and so that's sort of where the pixel side of it comes, right? So we have these two things that go on. We have geometry in the form of vertices, and then we have fragments in the form of pixels. Think of those like that. So that's why they're so important. All right, pardon me for bumping my microphone. All right, so referring back to the lecture that we had last time, and again, this is from the game architecture class normally, but we'll go through this a little bit. I'm going to hop over things. Some of them I'm going to skip over. A little bit about the scene representation, because we're not quite there yet in terms of class, right? So far we're dealing with simple primitives. We cleared a screen, we drew a triangle, we drew a point, very, very simple primitives. Eventually, from those we're going to be able to build larger structures, hierarchy, things in a scene, and so on. But a lot of that has to do with an overall architecture that's generally going to be part of maybe a game engine or something where we have multiple models that we're perhaps managing, and each one can be animated and doing different things in its positions and scenes. And there's a gray area between where we are now and where you'll eventually get with that. But we won't talk about it too much just yet. Right, so this idea of objects and scenes and so on. Just be sort of aware of things. The one good question that came up was this notion of like, well, as you're programming so far, in some of your programming, you step through all these things, and you had your linking, your compiling of your shaders and linking them into a program, and it seemed like you were doing a lot of stuff, and then inside your loop, you were doing certain things over and over again, that nothing was changing. Why would that be? And that's precisely because of these other things. As we get into shaders, as we get into scenes and objects and more complex architectures, you can imagine that you're going to ultimately have lots of different geometry, lots of different models, and lots of different shader programs, and lots of different sort of materials and so on in your scenes. So some of the things we're doing right now, even in the OpenGL program, are aimed towards that degree of flexibility later. So bear that in mind as well, hopefully. And ask a question at any time. So let's see. I stare at too many screens here. All right. Okay. We'll keep going. We won't talk about tessellation so much right now. What tessellation is, we'll just say sometimes you have geometry that needs to be broken down into either simpler or more explicit geometries. That's what tessellation is. We'll talk about that later. What we will talk about now is this thing called triangulation. We're not going to do any triangulation, but we're going to view triangulation as being a motivating factor behind the architecture of OpenGL and a lot of the other modern graphics hardware and graphics programming these days. You'll notice we have certainly our basic unit, aside from pixels, is we had this idea, we drew a triangle. And if you're familiar with gaming over the last 10 years or so, chances are you've noticed that games and graphics and presentation of pixels on the screen ultimately seem to be in this kind of triangulated form, right? Models are made up of these polygons, and generally, everything, if you look back at, PS1 style games and earlier games, it was far more obvious that things were made up of, complex geometries were made up of generally of triangles, in some cases quads, which would be, of course, a polygon with 4 vertices. But we like triangles for some reason, right? We're making more complex models out of simple geometry, simple structures, simple primitives. You'll hear that word a lot. And usually that the foundational primitive in a lot of computer graphics is that triangle. Now, there certainly are other fields, like if you went into a more pure computer graphics and you're studying ray tracing and you're studying, purely computer vision and image processing and so on, you may get beyond triangles because triangles is just a convenient way to represent things in a simplified form, but they're very powerful in that regard. So there are other ways to do it, but triangles are sort of the main building block we use these days, and they've become certainly very popular and powerful in light of the way that we can process them in modern graphics cards. So we like triangulation, we like triangles. And this idea of triangulation is basically tessellating or breaking down a surface into triangles. Why do we like triangles? Triangles are fairly ideal to work with. As it says on the slide, almost all modern graphics hardware is designed for triangle rasterization, right? We draw the triangles, we can draw them on the screen because we know how to rasterize them or turn them into pixels, right? If you think about a triangle, triangles just like a tripod, a chair, chair or table with 3 legs. It's perfectly stable because the 3 points within that triangle all are on the same plane, right? With 3 vertices, the polygon that's expressed by them is basically they're all on the same plane. You wouldn't have any bends, you wouldn't have any curves, you wouldn't have any folds or creases and so on if you only have 3 vertices, which makes them fairly ideal to deal with, right? Does everyone kind of get that, right? If I had a triangle and I put like I said, a stool or a table that has 3 legs on it down on the floor, it's always stable, right? Because it intersects with that floor, that one plane that it sits on, right? So we like that. That's wonderfully stable. It doesn't have a curve. It's not a complex surface. It's a very simple surface, right? Also, it's nice because we can easily kind of triangulate things like breaking more complex surfaces down into series of triangles or triangle meshes that then can form our complex surfaces and our complex objects, right? Because of that, most all modern graphics hardware is designed for triangle rasterization. There were some very notable platforms that did not, and some people will say as the rise or fall or the demise of the Sega Saturn, that it actually used quads instead of triangles. Early on, they thought perhaps it would be more powerful for using that. But in the end, a lot of people found the PlayStation 1 a lot easier to deal with because, in fact, it was a triangle-based GPU versus the quad-based one on the Saturn. That's a bit of ancient history. Now, it turned out later on when they went from the Saturn to the Dreamcast, the PowerVR or the NEC graphics architecture that they used as well in the Dreamcast also had to have some bit of backward compatibility with those quads as well. So anyway, that's history. These days, largely we're dealing with triangles. So we'll put that other stuff behind us. Triangles won with regards to most modern computer graphics. That's why it's in the slide. But there are still cons to triangulation. Tessellation is normally fixed, right? And that's, well, the issue is if you have a model that you express strictly in form of triangles, how do you then, improve that model? Once it's in a certain shape, things like curves, things like splines, things like Bezier patches and so on, the nice thing about them is you can compute them at whatever degree of complexity you need to. So that's a good and bad thing because of that complexity. But in the case of triangles, once you have a triangle is a triangle. right? You have to, it's not like it's got, you can decide to show more of it or less of it, whatever. It's a triangle. It's kind of fixed, and that can be an issue. There are ways around that. If you have a low poly model, typically it is going to look blocky, especially as you view it from angles and things like that, because as you view the edges of it, you'll start to see those lines depending on how low poly it is. Now, there have been a lot of modern things added, things like level of detail, LOD, where you might have different representations of a 3D model in all sorts of different cases, and that might be more and less complex. And so there's ways around that. But fundamentally, when you have a model that's based on triangles, it is what it is. So with this, good and bad. All right. So we have triangles. We'll just accept that triangles are our friends. All right. So the cool thing, like I said, they're a good representation. They're always planar. Now, some things you need to potentially do with them. There's some things that are useful to know about them. There's a couple of things called the winding order. Now, a winding order, you might not think about this, and implicitly it doesn't really matter so much, but as you draw triangles and the architecture is going to consider, well, how do I move around the edge of a triangle? What order do I consider the vertices in? Do I do the clockwise? Do I do it counterclockwise? That might be referred to as the winding order. And then there's also this thing called normal calculation. Right? So given that we have a triangle, we start to think about things like, well, the triangle has a front and a back, sort of. It's got the plane, but which way is it? Is it facing me? Is it facing away from me? And that's where we start to get into normals. Right? You can even have normals at each of the vertices, which is a little bit more complex. But if you think about the surface of the triangle, it will have a direction that it faces in. Right, a front and a back, and depending on how your graphics engine and what you want to do with those triangles, imagine the inside of that dolphin model that I just showed you. Right, this dolphin has an inside, so there's an inside surface and an outside surface as far as each of those triangles is concerned. So it might have a normal that points outward. We say, okay, that is the normal of the triangle. That indicates what the forward-facing or the outward-facing face of that triangle is. Right, so that's important as well. Start to realize that having some math, being able to do some math might be a good thing. Right. So here we are. We can talk about our triangles and how we represent them. The representation, pretty straightforward. With a triangle, you have 3 vertices, right? Vertexes, right? Which is why we have vertex shaders, because ultimately that's going to be the basic thing with regards to geometry, how we calculate, how we work with geometry. Right, so we have 3 points, each known as a vertex. You might think of the vertex as a location, and so far in how we're talking about them and how you've dealt with them in your first programs, largely that's all they are. They're an X and a Y and maybe a Z location. Right, so they are some point in space. However, as we get more and more advanced, there's going to be more information at those vertices or sort of at those points, and that's going to become more complex. Right? So we're going to have more information than just the location of a vertex. So you sort of, at some point, you have to think of the vertex itself as being an entity and not just being a location. A vertex is an entity that has a location, but it's not the only thing that it has. And that will be important as we get into, also getting into shaders, right? Because we're going to process those vertices in a lot of different ways, potentially, okay? So, like I said, they're always planar. We have this winding order, potentially, which is, okay, how do I work my way around? And normally this is the first hint as to what the front and the back of the triangle is, right? If you wind in a certain order, you say, okay, if you take, if you're using various, think about physics in certain ways, certain operations and things, when you have a winding order, you have the right-hand rule and things like that. You can say, okay, if I wind in this direction, then the normal points in this direction, right? So if I travel around and I draw the triangle such that, vertex A, B, C go, in this winding order, then I know then the normal might point out, sort of thing, right? And that's also how we can get that by crossing edges with one another, but knowing which one is in going in which direction there, right? Don't worry about that too much yet. that'll become more important. But it does let us know that we need certain types of math, cross products, eventually dot products. We'll talk about that in terms of the math we need. So this is kind of motivation for that math. So let's talk about vertexes a little bit more. Now, so we have a vertex, you have a model, you have a triangle. A triangle has 3 vertices. So it's pretty simple. It has 3 vertices. It has how many pixels in it? Anyone? How many triangles? How many pixels does a triangle have in it? No idea, right? You shouldn't have any idea in a particular, because how would you? It's going to be entirely dependent on, let's see, I'm going to go to general here. Okay. Unless we establish some sort of resolution, you can figure out the area of a triangle. Certainly a triangle has area, but even then, how do you go from area to number of pixels? Right? So that was a good attempt. That was as close as you can come to the number of pixels. If you knew exactly your pixels per inch or pixels per, you could probably figure it out. But it is going to be, ultimately, it's the resolution of your screen, and potentially even, what if you scaled that triangle, you moved that triangle, you rotated the number of pixels that you need to draw for that triangle. It might change because of its orientation on the screen, which is kind of interesting, right, as we get into graphics. So it's tough to say exactly. The answer I'm looking for right now is a lot, right? Certainly more than 3. That's the important part. That the number of pixels you're going to need to render or process or shade is going to be a lot more than 3, right? So that was, pardon the confusing question, right? So a vertex shader, in the case of a triangle, we know that it's probably going to process 3 vertices. Most of your programs have, been responsible for processing 3 vertices and some unknown number of fragments, some unknown number of pixels. And ultimately, that's one nice thing that the hardware does for us, is it kind of translates in between when you calculate, you do your calculations as part of that stage of the pipeline, the vertex stage of the pipeline. It then knows, okay, based on that, how many fragments will there be, and it will call the fragment shaders for each potential fragment that needs to be drawn. Right? So that's kind of how things work down the pipeline, right? So you have, on the one hand, you have a vertex shader, which is processing each vertex that's part of the model. And then ultimately, with regards to translations, transformations, rotations, everything, between there and the next stage, we know, the graphics hardware figures out for you where all the fragments are that result from that, for that polygon, for that triangle, or for that mesh that you've created from those vertices. And then you start to fill in, right? So on the one hand, you can think of it as being, okay, here's the one that's sort of establishing the geometry and what's at each of those vertex locations. And then the other part, the fragment shader, the pixel shader, is what fills in everything on the surface of that triangle, right? So that's the relationship between vertex shaders and fragment shaders. Does that make sense? Vertex shader has a very important job to do. It's going to be called generally a fixed and predictable number of times, whereas the fragment shader is going to be processing a lot more, almost pixel level kind of operations. We don't know exactly how many they're going to be running, and they have to be running a lot more, right? There's a lot more of them generally. All right. So they be sort of leaner. And if you were designing an architecture, which would you want? If you said, okay, I can put 20 processing units on my GPU hardware that I'm developing, you might say, well, okay, I'm going to divide that up and say, well, 15 of them are going to be shading units and 5 of them are going to be vertex units, because that's where the balance is going to be, and that's what hardware designers often do. All right. How are we doing? I don't have a clock sitting right in front of me. So 12:52. Keep myself on track here. All right. So each vertex can contain a lot of different information. Normally, the first thing it's going to contain, of course, is a location in the world. I shouldn't say on the screen. It's in the world. There's a location for that vertex. That's part of it being, the model of whatever it is model. If it's a triangle, it is a vertex of a triangle at a specific location somewhere in the world, according to some kind of arbitrary scale. So, but you have some sort of position. But the other information that you could have with it, and hopefully if you have been playing games, or if you've been looking at games and looking at any sort of things on the screen, some of these terms will make sense to you. Some of them might be familiar, some might not be. Okay. The first one we talk about after that is generally not the first one after it on this list, but this important one. So we have position. We knew about position. That's an important one, right? X, Y, Z. And the next one I'm going to actually refer to as being the next most important is color, right? So imagine you were able to have a color at every corner of a triangle. Now, normally it might be all the same. If it was a flat triangle, if it was a red triangle, well, the color is just red. And in our program so far, we've assumed a fixed color because we've only had position information about the triangle. We haven't had any color information other than what the shader came along and kind of put on it. But you can imagine that every vertex might have a color, right? Then there's a lot more complex things, right? In addition to that, there's this next thing called UV. Now, UV has become even more complex, and that's sort of a coordinate. It's a sort of like we have an X, Y, and Z, but we also have UV. So we have UV, X, Y, Z. How did W get? Well, W is just confusing to read, which is maybe why we don't have W. So we have U and V, which is some other kind of coordinate that's going to be useful for a lot of things, particularly if you're familiar with texturing, right? If you have a texture that you want to put on a model, a texture might be yet another frame buffer or some other buffer, image buffer like we mentioned last week, right? And in a 2D buffer, like we mentioned last week, normally you had an X and a Y, and an X and a Y could give you any particular location within that frame buffer that you could then pull information from in that sort of two-dimensional array. So U and V are generally going to be the coordinates of that vertex in some other array. So it might, quite often it's in a texture array. So if you have an image that you're going to put on a triangle, for example, you have the coordinates in that image that are then going to get mapped into that triangle. Learn the words, be familiar, be aware of them, and then they'll sort of make sense as you start to encounter them in the text and as you start to use them. Okay, so the key there is that UV is your friend, and it helps you to, when it comes time to do texture mapping of polygons, when you want to put pictures on your polygons, pictures on your triangles. We'll do that pretty soon, right? But if you want it in simple hardware, simple graphics hardware and simple models, maybe you don't have the UV at all and you just use color. Or maybe you don't even have color on a vertex basis at all. Maybe you just have solid colors, but you'll see. Then we have other things as well. Normals. So each vertex might have a normal, which is going to determine kind of how it presents itself in space, and that'll help you figure out, okay, how does it, as we have intersecting triangles and so on, or conjoined triangles, how they fit together. Binormals, if you can figure out, which of both directions. Tangents. Other interesting ones like bone weights. As we get into more complex models, you might have a weighted point, and then there's things about lighting, etc., etc., etc. So vertices can become complex rather quickly. Okay, they're not just location. We're going to start with location. We'll have to leave that for later. Normally, pardon the pun, until we get into a model that might be sharing vertices, right? That's where it starts to get interesting, where we're sharing vertices, and the vertexes themselves are the entities that ultimately, it's not about the triangle, it's about the vertices and where they are with regards to the model. where the inside, the outside, and in that case, we need an explicit normal for a vertex because it is just a point, right? And then you can kind of think of that as the normal of that, defining a vector where that vertex is, and then where it considers things to be out from, right? So it's not so much a geometric concept as it is a convenience for what we're going to do in modeling. Does that help? Does that make sense? All right. So some of these things, certainly, there's going to be a big difference between kind of fundamental geometric concepts and the convenience it offers us to have an explicit thing at that point, right? This sort of graphics is more, it's always about simulation. It's always about like helping us get there step at a time, right? So, you know, imagine you had, let's see if I can do this. If I have a, whoops, that's not the one either. Let me do that. If I have this triangle, and this triangle, and I have a mesh, it might be useful for me to know that this vertex considers itself to have a normal facing in a certain direction, right? So that's why it has potentially a normal, or, you know, so we know its orientation as opposed to having to have, you know, compute a specific normal for each one of those. It's partially convenience, partially, you know, making these vertices and models more compact and performant. Right. You'll see that in action. Another question? Yes, that's one of the things you can do is you start to have vertexes where they're not necessarily flat, where they're not representing necessarily, like as we get into bump mapping, smoothing, height maps, that sort of thing, then you're going to want to know, potentially you might have a different normal, and they're cheats. They are cheats, right? Triangles are normally flat, but your model isn't flat, and ultimately we might be doing a lot of really cool tricks to make what seems like a flat model to be much more complex it is. There are things like bump mapping, height mapping, two that immediately jump to mind. And then you can do things like say, well, okay, if this surface is curved, if this triangle is actually trying to represent a curved surface, if I have three different normals and I interpolate those between those normals, I can smooth out the surface of a triangle. But that's getting ahead of ourselves, right? So, Lion, it's a good point, and that's absolutely right. It's one of those, if it's, now, like I said, fundamentally a triangle is a triangle. And what would a smooth triangle be versus a, you know, flat triangle? Aren't all triangles flat? Yes, they are. But if we're trying to be more efficient, well, or more flexible in what we're doing with these, and then you can start to make that jump from triangle-based models to a model that's actually made, say, based on a point cloud, and then you have vertices all over the place that have enough information about them to potentially represent something far more complex. You know, if each of those vertices is actually a control point for a spline or a complex surface, now we're getting even fancier. We can go down that path. So let's not get too jagged. But good questions. Does that sort of help at least? I know I'm leaving a lot of gaps in there, but that's basically what's happening, right? Our simple models, we leave the gaps for now with flat, and then if we have these more potentially complete or complex entities as vertices, we can fill in those gaps differently in more interesting ways later. You know, say if we had a normal at each point on a vertex, we could turn it into a smooth surface instead of just a flat polygon. Can I get a thumbs up to move on? So, or if you have any questions, do blurt them out. It's an interesting topic, and certainly things have gotten a lot more complex and capable these days. But let's back off. Let's take a step back and work our way up to those. All right, we'll work up to that. Let's just look at start with the simple formats and say, okay, let's assume, because we're going to talk about flat shading. First off, our first type of lighting is to be flat shading as opposed to Garot shading and more complex lighting models and so on. So we're going to get a lot of mileage out of triangles, especially with, you know, by adding vertex attributes. Okay. So, vertex attributes, vertex formats. What's in a vertex? Lots and lots of good questions, lots and lots of good information. Now, normally, you can think about them at first. The simplest sort of vertex and the conceptually purest form is that, yes, a vertex is just a point, right? It's just a point in space. So for that, we would just need a vector, a three-dimensional vector saying, okay, where is that vertex in space? Right? So that's our simplest vertex format would just be that. A lot of time, I don't know why, maybe we should put the simplified, but I'll show a simplified version of this. Yeah, we'll talk about this way. I'm going to skip a little bit of information there because in the program it'll make sense. So a vertex, the simplest form would have just a position, but a lot of the time these days we are assuming that we have textured polygons. So we're combining the geometry not with just a single color, but with some sort of texture somewhere, right? That's almost a given these days with regards to capabilities. Everything's textured in your games. I mean, how many games are, well, the look of a low poly game might have certain non-textured polygons, flat shaded polygons, but now the norm is really textured polygons. So we almost always think of vertices as having a position and a UV coordinate for its texturing. But you could just have a vertex that's just a 3D position. So a position is actually 12 bytes, right? There's actually going to be a set of, in this case, we're going to have, 3 numbers. Each one is 4 bytes. So 3 times 4 is going to give us our 12 bytes, right? So vertex has 12 bytes in it. We're dropping way down suddenly to like low-level stuff that you may have never had to worry about before. But yeah, that's OpenGL, that's graphics hardware. We're going to deal in bits and bytes and buffers and that sort of thing. So my apologies. So we have a vertex consisting of 12 bytes of information here, which is our 4-byte float for each of x, y, and z, right? So there's x, there's y, there's z. There's our 12 bytes somewhere in our buffer. Right, we have a buffer with actual bytes in it. And the next thing we have in there, potentially, if it is UV, we're going to have a U and a V, and we have potentially a floating point number for each one of those. So we have a X, a Y, a Z, a U, and a V. And that is one vertex, right? That is the format of the vertex, X, Y, Z, U, and V. And the example here you see next, okay, well, there's another position and another UV next to it. Yep, that's the one for the next vertex. Right, because we have a buffer full of vertexes. For a 2D position, would the vertex still store the extra 4 bytes for a Z position? Not necessarily. Not necessarily. You could set this up, right? The cool thing about the programmable pipeline and programmable shaders is that we're the ones defining this, right? You could even change it to not be using floating point numbers if you didn't want to. That would be kind of reckless, but you certainly could. You don't have to have X, Y. It could be Y, Z, and X if you wanted. Or X, Y, Z, and some other, maybe you have your own coordinate system that you want to use. They get a little crazy at some point. But we're actually defining these, right? We're defining this. This is just the most basic kind of example of a vertex and what it might have in it. Right? So we have our basic format. This is 3D hardware, though, so we're kind of optimized for 3D, so normally you might do that. Chances are you're going to have 3D positions, but you could do the other way around. Somehow you're going to then have to calculate the Z, but you could. So for now, let's assume that we have 3D, X, Y, Z, and a U and a V. Now, here in the lecture notes, and this is one of the things that I had a problem with in trying to discuss it all in game architecture, is that we kind of dove right into the thick of OpenGL, and we're going to have more time to look at individual formats here. So let's sort of dissect this first pair of things here. Okay, So in OpenGL, we have the flexibility to define what is in each vertex, just like you asked, right? And what this is describing here is actually it's telling OpenGL about that structure, right? That's explicitly what it's saying right here, right? So the vertex GL vertex attrib pointer, we're going to say, okay, OpenGL, I'm going to let you know that there's a buffer full of vertexes, and I have to somehow tell you what is the structure of that? What is the format of it? How do you pull stuff out of that so that you can pass it on to all of these shaders, right? So here's how it's going to translate, how it's going to figure out from what you're providing to ultimately how this makes sense, right? And we do that by saying, okay, GL vertex attribute pointer. Now, hopefully off the top of my head, I'll be able to remember these. So you'll notice this first off is 0. All right. What 0 means is that this is the first of the attributes that it's going to have. So 0, that's going to be position. Position 0. Position is going to be our 0th attribute. There are going to be 3 of them, and each one is a float, right? So we're fundamentally saying, okay, there are 3 values, 3 floats there. Okay? That is telling it what the attribute is, how many of the thing is there, and what is that thing. So in your case where you said, oh, maybe I want a 2D position, you would say, well, 2 GL floats. But we're using 3 for this. Right? You could do that. GL false escapes me for just a moment. Just it's not going to be... Oh, that means if there's a bit of translation involved, and we're not going to do... That's... we're giving it explicitly in the format, so it doesn't need to do some translations and permutations on there, so don't worry about that. We'll leave that out. Now, this next one is a little bit odd in that this is called the stride of the vertex. The stride of the vertex. You can go to sort of think of it as the size of the vertex, right? So this means, okay, how many bytes is there between each vertex? Right? If I wanted to move from one vertex to the next vertex, how far would I have to move in memory? Okay. So the simplest way to do that is by defining a vertex and saying, you know, what's it composed of, and then you can take the size of that, and then, okay, if you move chunk at a time, that'll move from vertex to vertex to vertex. So that's what we're telling it here, how to go over each one of the vertices, right? And last but not least here, the 0. It has almost all the information it needs, okay? But the 0, what that tells it is saying, okay, the position of this particular attribute within the vertex is at 0. Does that make sense? Right? If it's at 0, it means basically there's nothing before it in the vertex. It is the first thing in the vertex. There are no bytes before this particular attribute. It's at 0. And that's why it's good to have an example that has UV in it as well, because now we'll be able to sort of make some more sense of it, okay? So that told us if we had nothing but a simple 3D vertex, 3D position for the vertex, that would be all we needed. But if we have more, we need to say more. And here we'll do something to set up that U and V, just as an example. We'll say, okay, there's another attribute, U and V, that you're going to deal with, U and V. We'll just call that attribute 1. It consists of 2 floats. 2 floats. There's going to be no translation involved. To move from one vertex to the next, or even if you're looking at now, if you're looking at a particular UV, if you wanted to move to the next UV, you would just move that number of bytes, right? So it's not just how to move to the next vertex. It actually will tell you how to get to the next position of the next attribute in the next vertex, if you think about it. But then last but not least, it's saying, okay, now where within the vertex does that lie? And this is a little bit weird. in that it's saying, well, it's after 12 bytes, right? So you have to tell it, skip over these 12 bytes to get to the UV location. That's what's going on here. And this is a little bit odd in that it actually is expecting this to be a pointer. And hopefully, is everyone familiar with pointers? Pointers are your friends. I love pointers. Pointers are great. Okay. So it's odd. It is funny. OpenGL is sometimes odd. In this case, this is one of the weird situations where it wants a specific pointer for some strange reason. So this here is actually a null pointer. That 0 is a null pointer. And to show the pointer of the first element within there, we actually say a null pointer plus 12 bytes. It's kind of weird. But this is what OpenGL may very well want to see. So if you're getting weird errors about it complaining that you're not actually having a const char pointer, that's why. It's kind of weird. So congratulations. This is how we would actually tell OpenGL about something as simple as a pointer. Excuse me, not a pointer. A vertex with a position and a UV coordinate. Now, the next one, I'm not going to go into detail on this next one, but let's just say that if this vertex had a normal as well, a normal vector, this is how we would do that. So we would have 3 attributes. The first one is the position, the second one is a normal, the third one is a UV. And you'll see it has here this middle section that says, okay, now this one contains, another vector of 3 floats, and you can see there's calculations necessary to make sure where the stride is. The stride is the same, so size of vertex is different. It's calculated differently. And then ultimately that pointer is calculated differently as well. Right. So that got us our vertex structure. Now, if I were to come over to a program, and here is, I think this is exercise, or I forget if I did, did I call this exercise, or did I call, well, anyway, let's see. In looking at, let's look at your previous work, okay? And we'll talk about how that got done, some of the previous programs. And this was a real simple one. This is was one of the first where it actually did read the shaders from, well, let's see this exercise. I shouldn't show this. I should show the triangle one. Yeah, this is a good one. Go back to that. Sorry. All right. So in here, you may have seen that there was some setup. There was, this is, so this is 2.5, and let's run 2.5. I'll show you, I'll drag it from the other screen, hopefully. Hopefully I haven't messed it up and it runs. We have a triangle. Congratulations, a triangle. Right? Did everyone get that? Program 5? Hopefully you did. If not, tell me why. So in this, we had, basically one of the simplest programs, and it didn't really even set up a lot of vertices and so on. It was kind of, if you look in here, it's kind of, there are no vertices, there's no buffers, and it's kind of very odd. And that's because in chapter 2, we didn't really worry about the vertex attributes much, and the vertex buffers, the vertex buffer objects. We just set up the general vertex array object, and then kind of made the shaders do things in sort of a silly way. Hopefully we get to some more math today. How are we doing? Does everyone feel pretty good with where we're at? We're about an hour in, and this is going to be, we have a full hour today. There's no check-ins, so, or full 2 hours. So, all right. Anyone completely lost? Not yet. All right. This is really, I think I'd feel good about OpenGL doing it this way. So, all right. So here we are. Here we are in the ultimately 2-5 of the text. And what we've done here is we have our main program. We've set up GLFW. We've got some window hints, and we opened a window, made it the context, initialized glue. We've set a swap interval. Somebody had asked about this, the swap interval. Why is that? Why isn't the program just running as fast as possible? And that's because we have set it up to be sort of double buffered and for it to be vertically synced so that it only flips buffers when a frame is done being drawn on the screen, which makes things look smooth, which makes things look good. We'll talk a little bit more about that if somebody wants to, but we'll leave that. There's lots of, if you look up double buffering and frame swapping, there's some good information on that. But it is important. This is one of the reasons, using this swap interval and using swap buffers, it does keep the program from just running as fast as possible. It will run up to the refresh rate of the screen. Anyway, so it was a good question brought up. Go back to Discord and read that stuff if you need to. So then we have init. And init, of course, in this case is going to be one of the most important things because display, swap buffers, not a lot going on in the other ones. So in init, we did load 2 shaders and go back, work through 2-5 is an important one so you understand the basics of reading a file, loading in the shaders in that way. You have to think about it now. What's happening is ultimately, again, creating a shader program here, if I look in utils, right, it's all about loading each of the shaders. So we load them from their files, we compile them, we link them, they become a program. Sounds a lot like general source software development, right? You compile each component, you check for errors and so on, then you link them together, and then you can actually say, okay, run that program or use that program, right? So that's important basic stuff to be concerned with, right? So it's linking, compiling, linking, getting ready to use the shaders at that point. Right? I had a moment that I just, what was I going to say? Based on the code, I may have to come back to it. All right. So here we are. We're setting up the shaders. And so we're not running any code here when we say create shader program. We're just compiling it, getting ready to run up there. Oh, I remember now. If you've ever noticed, sometimes when you first load a program, it takes extra time, right? Even loading a game, it takes extra time and so on. Because literally what's happening is that the drivers for a particular set of hardware, these programs don't necessarily, the shaders don't necessarily get compiled until you're actually running the program, right? This is being done dynamically. So the drivers that are provided by the manufacturers ultimately are their own little compiler, linker, et cetera, everything it needs to do on the fly to make that run. So unlike most of program development where we're compiling, linking, and all that ahead of time, this is actually being done, and it's subject to how good your drivers are. That's how we can update drivers and suddenly magically new versions of OpenGL work, things like that, without reinventing the wheel necessarily. So anyway, so here our shaders are getting loaded and so on. And then we just say, okay, let's generate the vertex arrays. So vertex array object is the main way that we communicate back and forth between OpenGL. And then we just say, okay, let's bind that vertex array and say, that's the one we're going to use. Now, we haven't really done anything. We haven't set up anything, there's no data associated with the array. There's no attributes, nothing. It's just really, we just set up this array object and said, okay, we're going to use that one. And yet, this is capable of drawing triangles. Very strange, right? All that display is doing is it's saying, okay, use this program and do this. GL draw arrays say, okay, I'm draw some triangles, and I'm going to say, okay, start with triangle 0 and go to triangle 3. But I haven't really even said where are those vertices coming from? Where are those vertices? You know, don't I need to set them up? Well, that's why this program is really, really dumb, and I just, you know, it's really interesting, but in a dumb way. So GL draw arrays is where we're telling it, yes, start at vertex number or identifier number or index number 0, and you have 3 vertices to draw, but they have no attributes. They have 0 attributes. So you're still telling it, okay, hardware, draw 3 vertices, but there's no attributes associated with them. So how does it get them? Well, we've pushed that problem off to the Vertex Shader itself. So here's the Vertex Shader that's associated with that. And this is doing stuff that I would never, ever recommend that a real shader. I'm gonna reformat this just a little bit, just so I can kind of explain it a little bit better. And it's basically saying, all right, what's going to happen is, remember I said the vertex shader is going to get called for each of the vertices, right? So it's going to get called 3 times in this case because we told it there's 3 vertices to be drawn. It doesn't have any data associated with them, but it knows, okay, I'm going to draw you 3 times. The one bit of information it's going to pass is it's going to send this vertex ID, GL underscore vertex ID. So if you look at that number while you're processing, you can't do a print statement because you're in you can't print from a GPU through a shader. You have to be clever in terms of how you get information back. But the one bit of information it does have is it's actually being told what number, what index is that vertex. So we cheat here and we say, okay, vertex, if I'm being asked to draw vertex ID 0, I'm going to say this is the position. It's hard-coded in here, this 0.25, negative 0.2501, right? Hard-code that position in. Now we're going to deal with positions in terms of 4 vectors of size 4. We'll talk about that as we get into math, if we ever get to that today. And then it says, okay, the next one, if I get vertex ID 1, use this position. Otherwise, use this position. So it really has hard-coded into the shader, in the vertex shader, the actual position of each of the vertices. And this would be a terrible, terrible way to actually do. Imagine if you had to have your 3D model, an OBJ, which was a Viking warrior, 700,000 polygons in it, and you hard-coded it so that it would say, okay, vertex 0 is this one, vertex 1 index is. It would just be a nightmare. You wouldn't want to do that. You would never hard-code this geometry into the actual shader. What you would really do is you would set things up, read them in, create your vertex buffers and your vertex buffer objects in your program. That would turn it into the right thing. And then, because you're saying, okay, here's a collection of my 700,000 vertices, it would then know how to deal with them. Right? But in this case, up until now, it's doing a hard-coded, terrible thing, and it's creating this geometry. So every time the vertex shader runs, you'll notice the important thing is that it is passing back this GL underscore position, which is a vec4. It expects it to be a vec4. And that is the position that OpenGL is then going to use, the hardware is then going to use to figure out, okay, now I'm going to figure out all the pixels that are in between the vertices of this triangle, because we told it was a triangle, right? In our code here in main, we did say, yes, there's a triangle defined by 3 vertices. So that's what happened. So the vertex shader would come along and say, okay, for each one of those things, it's going to do this and pass a position to the next thing in the pipeline. Now there's a stage in between your shader and your it's not going right to it. So that's why it's not a one-to-one relationship. It's going to do some stuff in between. But then ultimately, the next phase, and this is also the simplest possible, but still useful. I think this is a useful shader compared to the other one, which scares me with the hard-coded thing. This is hard-coding a color. It's saying, okay, and it doesn't care. You'll notice it didn't do anything with the position. It didn't do anything with any other information. It wasn't smart about being passed anything. It does no array objects. There's no or array attributes or anything like that. It's not doing texturing. All it's doing is saying, okay, color. That's the output here. You'll see out vec4 color, and that's the output from here, right? A vertex shader, excuse me, a fragment shader can output lots of different things other than just a position. So that's why we were saying, okay, here's the out of that. So the syntax of this is a little bit different. So important out vec4 color. That's the result. And that's something that's defined so that Opengl knows, okay, this is the color of the pixel of the fragment that we're generating based on that. Right. So that's what happened in an awful way to do it that didn't really even use vertex attributes. As we get more sophisticated, for example, let's see, I should have had an example that actually used. Yeah. I should have done the chapter one, not the X. I'll show you. It'll be fine. It'll be fine. It'll be great. Okay. So we'll look at this just real quick. In chapter 4, we're actually loading geometry. We're actually using the attributes, vertex positions. So you'll see in here, I have a set of vertex positions that are in an array in my main program. A set of 108 vertex positions divided by 3 is going to give you your actual number of vertices in this case. And there's some clever things that can go on as well. The number of positions and the number of the number of positions doesn't necessarily mean an exact correlation between the number of positions and the number of vertexes. We'll get back to that one. It's kind of weird. But you'll see what it's doing here. It says, okay, to set up your vertices here, we have an actual array of vertices. Sorry. And now we are using buffers, right? So just like the other program, we said, okay, let's set up our vertex array objects. You have to set that up. But now we're going to generate some buffers to use actual data in there. So we're going to say, okay, in this case, we're going to generate one buffer. We have one buffer object here. And that buffer object ultimately is going to be the thing that contains our vertex attributes. So we have to bind that buffer as an array. And then we tell it, okay, here's the data. Whoops, didn't mean to do that. Here's the data in my current program, in my CPU program. Here's where it is. And here's how big it is. And then ultimately I tell it, okay, how is that laid out? Here's our friend, GL vertex attribute pointer. And this looks an awful lot like the one we discussed. 0, it's the first attribute, the 0th attribute. It is 3 floats. That's the position. And because it's, I guess we get it. I think we can get away with this being 0. Normally, this should be 3 here, or 12. Should be the size of that. That's kind of weird. But I think we can get away with it because there's only a single attribute. I think that's the only reason. So be wary of that. If you see any examples from the books that they're using 0 as the stride, I think that's only because they'll only work in the case of a single attribute in the array. And then after you set up the attribute, then you have to enable it to make sure that it happens. Okay. So that's the key difference as we're going to now from the simplest programs in chapter 2 to these what will be the more sophisticated ones in chapter 4, where you're going to be really working with models that are real models, or at least primitives and so on that have real attributes behind each vertex. We good with that? get better with my polls. All right. Great. People are paying attention. As you use them, it'll become far more, you become far more fluent in it. And then in the end, you're going to call GLDraw arrays. Now notice in this case, after we set up all these things, and potentially there's some more advanced things you're going to be doing in chapter 4. But ultimately, it comes down to the same thing. We're just going to say, okay, draw a set of triangles, a set of 36, a set of vertices that are defined by 36 vertices. All right, we have triangles, and this is the number of vertices, right? So if you took our 108 divided by 3, you get our 36. Right. A question. Is there a set list of stuff that we can send in with vertices? No. Ultimately, you define that. It will be up to you. That's why some shaders are far more complex than others. And you can dynamically do it. Within your program, within one actual game, you might have certain shaders that really only care about geometry, other shaders that really just care more about lighting and normals and things. And there's going to be other types of information too. There's going to be information that you pass into these. You'll start to see, let's see if I have an example of it here. These things called uniforms, okay, which is going to be another bit of information that you pass into the shaders. But uniforms are things that don't change on a per vertex basis, right? They're used by all the vertices that you're going to be working with. So it might be something in the case of like a rotation matrix or a transformation that a model is going through that you do once, or you use for all of the vertexes, all of the polygons, all of things, but you need to kind of get that information over to the shaders. So it will depend on the circumstance. But the things that I mentioned thus far, position, UV, potentially normals, binormals, different things about lighting information, and so on. If a fragment and vertex shader both have a uniform variable of the same name, do they share the data? In this case, when they are linked together into a single program, they can. Okay. Now you have to remember that the fragment shader is always called after the vertex shader, so you can't really send stuff back. Remember, a pipeline, this is the idea. If you have a pipeline, you flush, things go down, you can't get stuff back. So generally, vertex, then fragment, then so on and so forth. Okay. Normally, what's going to happen is, yes, there's lots of ways to send information down the pipeline, and you're going to be calculating stuff in the vertex shader that then is going to be used by the fragment shader. That happens all the time. That's fundamental, right? How much of it you explicitly use versus how much of it you whatever. But anyway, generally, the way that uniforms are used is that it's just a common thing. It doesn't change. You can't really change it in between this shader and that shader, but you can pass per vertex information down, right? Because you don't know, 3 vertices, which one of those, which iteration of the vertex shader running did something change that then got passed to everybody? It's tricky. So be careful. Be careful of that. I'm not ruling it out. And some of the more advanced type shaders, I'm not as familiar. Not certainly as you get into using ray tracing units and so on. Who knows? There's lots of room for more fun things. We'll get into that. There are definitely ways that information is passed through. We'll get to there. All right. Now, that's actually a pretty good segue. Let's rest for two. Let's take a sip of coffee for a second. And actually, the concept of the uniforms is a perfect segue into some of the fundamental math that we're going to talk about. Okay, because if you look here, if I look at the uniforms that I'm setting up MV loc, which gives me the location to put my MV matrix at. And then I have proj loc, which gives me the location to put my projection matrix at so that the rendering program knows about it. And then ultimately down here, I am pushing information into those uniforms. Into MV loc and proj loc, into those locations. And what I'm passing is this value, which is an MV matrix and a P matrix. And those we'll talk about in math. What are those things, right? So let's take a brief breath. Here's the hint, right? These are some important matrices. Right. Deep breath. How are we doing? Is the pace okay? All right. Some people are paying attention. Yes, question. Owen, you have a question. That's true. Because of it's kind of like, in the case of shaders, it's like programming in general. Shaders are programs, and they're capable of anything. And the types of things you might want to do with them, over the course of graphics development, we've kind of gotten to the point where there's a lot of very common things we do, like bump mapping and tessellation and so on. Trying to do all of that right now without getting to the basics of saying, okay, here we have a vertex. Let's get the vertex up on the screen. Let's shade that with a certain color. That's the fundamental thing that we want to get across right now. But know that those same mechanisms and those same expansions of those vertex array attributes and so on, they're going to enable you to do all of those other things as well. Okay. So the question I'd have for you is there in doing the let's see, as you start getting into the programs in the homework, and certainly that's going to be in chapter 4, we're going to be talking now about the math. And when I said we'll go into depth more later, some of it is literally the next thing with regards to the math. But there is a lot of things that just we can't kind of parallel process everything, especially UVs and textures and so on, right? The simplest thing is to say, okay, we have a vertex, which is a position. There's a processing unit called a Vertex Shader, which is going to say, okay, how do I get the location of that? And you might be thinking, well, why am I just looking at, I just have a number, that's my location. Well, I'm going to explain in the math now why that's not just a number, why your shaders need to do more. Okay. So hopefully after we get into some of the math, we're getting there, right? It's a chicken and an egg when it comes to some of this stuff, right? Is that okay? We'll try. If things are I think things will become clear as we get into the math piece. All right. So let's talk about math. Now, it is tricky. You're absolutely right to be asking these questions. And always part of the problem is, well, how much fundamental, do you need to understand the physics of optics and light and cameras and, the rods and cones in your eyes, why RGB, at some level each one of those things could be an entire topic, an entire subject, and a book could be written about each and every one of them. So we're faced with a challenge, and even just in developing this course, we've broken out all the OpenGL stuff, hopefully into enough scope that we can discuss it in the depth that it deserves, because it is such a fundamental thing. And to some degree, being on the game side of things, we're talking about these in a very kind of real-time computer graphics way, as opposed to a generalized conceptual computer graphics sort of way. So it's a compromise. We definitely have to make that compromise. A lot of computer graphics courses might not even talk about something like OpenGL. They might not even talk about 3D rendering. They might be talking about entirely concepts and then ray tracing and line algorithms and so on, and you really would get no experience with that sort of real-time aspect in OpenGL and eventually Metal and so on. So it is tricky, and it's a very good question, and I appreciate the question. And anyone, let me know if there's something that I've said, okay, we'll talk about that later, and I don't circle back to it in time where I've assumed I did. That's the problem with 3 classes simultaneously. But do ask. All right. So let's talk about some fundamental math, and hopefully this may clear up some of that slideshow. Here we go. Present from the beginning. And it's showing me, of course, on the every one of the wrong monitors. And because of that, in the interest of fair play and getting the job done, we're just going to go from this view here. All right. So this is largely the same math that's in the book. This is based on the math that you're going to be seeing in there, and those are the fundamental things in there. There's going to be a few particular areas that I want to talk about a little bit more in depth, and they're going to be, again, it's sort of like, well, how in depth do we go into quaternions? That's always my fundamental question. Quaternions. They're a imaginary 4D. A fourth dimension imaginary space that allows us to calculate rotations in 3 dimensions. How much of that do you need to understand to use them? Very little. You can just say, okay, use quaternions because they're good at this. And that's adequate for the majority of people in computer graphics. But, do we spend the rest of the course on quaternions as well? It's tricky. It's tricky. So we'll try to get there. Let's start with the basics, though. All right, 3D coordinate systems. We understand X, Y, and Z. That's our general fundamental way that we want to represent something in space, an X, a Y, and a Z position. We're doing it in such a way that it necessarily is not resolution dependent. We're doing this, we like to deal with floating point numbers. If you came, once upon a time, we were a lot more integer based when we dealt with just, pixel coordinates on the screen. We're not dealing with pixels. Don't think of pixels now. Think in general terms about 3D coordinate systems. So these are all floating point numbers, which we mentioned a minute ago. So floating point numbers are nice. And it might be that infinity is sort of, concept we don't need to deal with, but, maybe we're dealing in meters, or we're dealing in miles, or we're dealing in centimeters, whatever. Let's just think in raw terms here. We're floating point numbers that can be scaled up and down and so on. Very basic. So we have a 3D coordinate system, and we have this terminology that you will sometimes hear, and it's just good to worry about up front a little bit, called right-handed coordinates versus left-hand coordinates. Whenever we're talking about computer graphics, we have to deal with coordinate systems a bit as just sort of a warning. All right. If you think about your screen and you say, oh, okay, there's an X and a Y on your screen, where is 0 on your screen? Is it at the upper right corner, the lower left corner? Does it, is the upper corner, I can do this, up here versus down here, versus over here. Which is 0, 0? And this is probably not 0, 0, right? This is usually we don't say 0, 0 there or here. But over here or over here, you know, maybe where it sort of makes sense. That's increasing. That's increasing. But a lot of the time we say 0, 0 is up here because in the terms of where things lay out in memory, we actually draw, you know, across a line, then the next line, then the next line. So memory location-wise, that makes sense to be 0 as versus that being 0. So there are some arbitrary determinations on kind of where the origin lies. And just as much, there's also saying, well, okay, what direction is positive z? Is positive z into the screen or out of the screen? Right? If you've used Unity versus Unreal, I think the two, I haven't looked at Unreal long enough to remember now. Or actually, sorry, I'm thinking in terms of OpenGL versus DirectX. Now, DirectX is Microsoft's Windows kind of specific stuff for graphics, Direct 3D and so on. And of course, you can study that all on its own versus OpenGL. And each one of them, one is a right-handed coordinate system, the other one is a left-handed coordinates. Now, OpenGL, I think we're in the right-handed coordinate system, which basically means with positive x to the right, positive y pointing kind of upward on the screen, and then z being out of the screen. Whereas DirectX, Direct 3D, z points into the screen. Right? So increasing z is into the screen versus increasing z being out of the screen in our case. So that's a very fundamental thing, right? Hopefully we get that one. That's a give me. All right. Switch back to my normal pointer. So we need to somehow deal with these. We need to represent these 3D values, numbers, points in space, concepts, right? So we have 3D points, which is typically an x and a y and a z. And that can potentially represent any point in the space, but it also can represent what we call a vector, right? A vector is sort of a triplet or a quadruplet. That means, okay, this is something, it has a quantity in x, a quantity y, and a quantity in z. And we're going to use something called homogeneous notation, which allows us to work with the 4D arrays that we need to, the 4D matrices, the 4D matrices we need for the type of 3D geometry we have. I hate to say it again. We'll get a little bit more into that later in terms of why we're dealing with 4D numbers, four-dimensional matrices as opposed to 3D matrices. We'll get there. So, but generally, we have these vectors that we're using to represent these, what could be 3D points or vectors, right? Because they are units that have, fundamentally they have a dimension. They have 3 dimensions to them. Some dimension in x, y, and z. And in the case of a homogeneous notation, we have just tack a 1 on the end, right? If you're familiar with linear algebra and you say, well, okay, if I'm going to be multiplying vectors and matrices and so on, you know that, one of the rows and columns, we need to have, ordinality sort of match up, doing 3-dimensional things against 4-dimensional things doesn't work out so well. So that's why we're dealing with homogeneous notations, and because matrices used in 3D graphics are typically 4x4. I'll tell you this one right away. This is one to really think about because it sort of blows my mind. And this is why this makes sense, sort of makes sense, or maybe not at all. So an interesting thing is we have, if you think about 2-dimensional games, you have x and a y. This is a side note. An x and a y, and something rotates. You have an object in your game. If you've ever written a 2D game, you have a sprite, and your sprite can rotate. Now, your sprite doesn't rotate in terms of x or y, right? Your sprite rotates in terms of z, even though you're in a 2-dimensional game, which is weird. Seems a little bit weird when you kind of think about it, right? You have 2D, but in order to rotate, you have to think in terms of that relationship between these two things. You need this kind of complex relationship that gives you that extra, the ability to express that. Okay. So let me just put this as a footnote for later to say, well, imagine if you wanted to express a three-dimensional rotation, an arbitrary rotation in three-dimensional space. I'm going to say, well, doesn't it stand to reason that you need a higher order dimensionality, just like we need x and y, we need 2 dimensions to get our rotation in z. We have an additional kind of 3. In order to rotate in 3D space, we actually need to think in 4-dimensional space. Okay, that's just something to keep in the back of your head. That's definitely some more advanced math stuff. That's the chapters and chapters, if not books, are read about, those written about those sort of things. That's the hint of quaternion and 4-dimensional space and 3D rotations. But so suffice to say, there are reasons to be working in 4D 4x4 matrices, even though we're in 3D graphics, for some of the same reasons that in order to, that weird relationship between rotations and higher order dimensions. Sort of makes sense. It sort of doesn't. For those of you who are really getting to become mathematicians, someday you'll say, oh, Eric, you oversimplified it way back when, which I am doing, but it's the hint. So hopefully you are relatively familiar with matrices and linear algebra. Oops, I almost forgot a quote there. All right, it's probably fresher in your minds than it is in mine, perhaps. But this, we'll talk about kind of the basics for now, and the basics, really the important part for us now. All right, so we have an identity matrix. It's our friend, right, which has 1 as the diagonal, which means if we multiply anything times the identity matrix, we just get the original back, right? So no hating on the identity matrix. Pretty straightforward. And ultimately, we need to be able to handle matrix multiplication and multiplying a vector by a matrix. Now, there's the hint, first off. In order to multiply a 4D matrix by a vector, we need that also to be a 4D vector. We needed that homogeneous form. Okay? We're good with that? Very simple. We take x, y, z. We multiply x times a plus b times y plus c times z plus d, because d is multiplied by 1. Right? And similarly, so d, h, l, and p, the cool thing about d, h, l, and p, they just wind up being added by themselves because of this one term down there. And that's going to be important in a second. Not in the vast future, in a second. All right. So in addition to being able to multiply matrices times vectors, we're going to want to multiply matrices by matrices. Right? None of this should be earth-shattering. It's all pretty straightforward. And the nice thing is that we're going to use this to combine things like combine rotations and translations and transformations into more easy to deal with operations. Right? Why do we need to concatenate or to multiply matrices times matrices? Well, we'll get there in a minute. So, matrix multiplication is associative. This will become useful later. Trust me, right? What we want to be able to do is, if we want to figure out where a certain point is, we may have to multiply that point. Ultimately, it's going to be multiplied by various matrices. But the nice thing is that we can use association to say, okay, the point times the product of those 3 matrices is the same thing as if we multiplied that point times each of them consecutively, right? It just winds up being potentially a lot less math if we're dealing with a lot of points, a lot of vertices that we can pre-calculate the combination of those matrices for, right? Now remember, a model in a 3D model might be hundreds of thousands of vertices, hundreds of thousands of potential points. And if they have some common set of transformations, translations that are expressed as four-dimensional matrices, it's nice to be able to combine them that way, right? To use this associative property of the multiplication, right? So there we go. That's the nice thing. Equivalently, we can say ahead of time, we have matrix 1 times matrix 2 times matrix 3 gives us matrix C. And then ultimately, if we need to calculate something for that new point, we can just multiply it by that one matrix as opposed to so on. Right? So in this example, matrix C is often called the concatenation of matrices 1, 2, and 3. Matrices 1, 2, and 3. Right? So that's the basics, the first basics. So we need to multiply vectors times matrices in order to be able to transform points. To get a new point that we have transformed and translated, what that means, we're about to discuss. But in order to manipulate points, we need to be able to perform basic matrix multiplication on those vertices. And then in order to combine higher order operations, higher order transformations, we want to be able to combine them through matrix multiplication. Right? So, what's happening in a 3D game? What's happening in 3D graphics? Ultimately, we're saying, okay, here's a vertex somewhere in space, or maybe, actually, here's a vertex that's part of a model, or part of an object, or here's just a vertex. And what I need to do, in order to put that on the screen, in order that to do the right thing, I might have to do a number of different transformations to it. That might be the result of looking at it through a certain type of camera, which is going to have some sort of scaling and distortion. It might have to do with its object based on, my Viking model turned to the left, or translated, or shrank, or rotated. That's the turn to the left part, right? So there's a lot of different potential transformations that can be done to a particular point. And in order to transform a particular model, we are going to have to do those sorts of things over and over and over again to each one of the points, each one of the vertices in that model. So we have a convenient way to describe these transformations as matrices, and we have a couple of ones that we're going to refer to. We're going to break them down to kind of so they'll sort of make sense. So the first one, the simplest one, is the translation matrix. So a translation is if I want to move something in space, right? I have a point, and all I want to do is move that point somewhere in space. It doesn't, or a model even. Let's say model or a triangle, and I just want to move that in space, right? All I'm doing to that is I am adding an offset, right? Imagine I have a vector, and I would ultimately add an offset to that, right? So how do we represent that translation as a matrix that we can use? Well, because we're using this homogeneous form of x, y, and z, right? We have these guys here. Fair enough. Right. Things like scaling and rotation and more complex operations are really going to be the domain of this portion of our matrix. This handy row, or handy column here, ultimately is providing us with a simple way of expressing a translation, right? So if I have x, y, and z that I want my point in, and I have my translation matrix here, and ultimately I have some new x, y, z that comes out. If I multiply the two, you'll see that I take x times 1 gives me x, nothing times y, nothing times z, and then this x transformation here, sorry, I didn't mean to cross it out, is multiplied by 1, so this becomes here, right? So now our new x is the original with this translation, and it works through the rest. I'm not going to go each way, but basically we have an amount to move in x, an amount to move in y, an amount to move in z. It's a pure translation, right? So this is a pure translation matrix, especially because we have effectively the identity across there, right? So, one out of the way. The nice thing is that we are using a GL math library, GLM, that allows us to perform translation. Right? You can set up a translation matrix. This will set up the translation matrix, and then you just multiply the translation matrix times this vector. Right? You take this here. Sorry, I'm getting messy. Look at that. You guys can see the yellow and all that well enough, right? So this portion here, we plug that in here. We get a translation matrix back, this new matrix, that we can then multiply by our vectors and give us our newly translated point. Right? That's the simplest one. We're just getting warmed up. So let's, can I double click on that? Wish I could just double click and erase everything on the screen though. Anyway. Go back to pointer, and up next. Scaling. Okay. What is scaling? If I have imagine I have again, my triangle. It makes more sense when you're talking about objects or primitives as opposed to points. If you scale a point in space, it is going to move it, right? There's going to be motion involved. It's going to move towards the origin, right? As you scale something down, scale point down, it's going to move towards the origin. Up, it's going to move away from the origin. If you translate it, it's going to slide uniformly from that, right? Whereas in the case of a translation, or in the case of a scale, it's going to be just kind of moving out and away from the origin according to how you're scaling in each dimension, right? So a scale is a three-dimensional operation. And now our scaling matrix, now we're going to have a direct impact on X, Y, and Z, the original, because they are going to be, again, sort of pushed or multiplied along their original axes, right? So if we want to scale X, we have this number here. We have a scaling factor for X within our matrix. We have a scaling factor for Y, a scaling factor for Z, and 1, again, because we don't want to mess with that one. So our new X is going to be X times the scaling factor. Same for Y, same for Z, and of course our friend, the 1 down there, all right? So if I had 1s there and I multiplied by that, a uniform matrix, scaling by the uniform matrix doesn't do anything because everything remains 1. If I had 2 across for X, Y, and Z, everything would move twice as far. Basically, I would increase the size by 8, right? Because it'd be scaling in 3 different dimensions. But it'd double in each of its dimensions. Right? So if X was 1, if our simple point here was just at 1, 1, 1, and I said, okay, scale to 2, 2, 2, it would just get multiplied, or 3, 3, 3, right? It's just a straight multiplication, so that point is going to keep moving out and out and out and out along that vector that it originally was. That's kind of cool, right? It's basically scaling a vector. We're increasing the length of a vector by doing that. If you think of the point as a vector and you scale it, you're scaling the whole vector if you scale it uniformly. And again, GLM has that for that. I have to double check my time. 2:06. Oh my gosh. Whew. We're running out of time. Well, this is why I underestimated thinking that maybe I could cover most of the math stuff in one lecture, which I did not. Let me try to go through, introduce this part, because ideally, well, we'll pick up where we are, right? There's the third basic transformation type of matrix is going to be the rotation matrix. And it's going to allow us to kind of rotate things around in space, right? And this is going to be the simplified form. For now, you'll notice we have 3, and this is where it's weird and why that 4D stuff that I talked about turns out to be important. in order to normally do rotation, if you wanted to rotate x by a certain number of degrees, you actually have this much more complex relationship, right? Because x is affected by y and z, y is affected by x and z is affected by x and y. So it's kind of crazy. But ultimately, these are the rotation matrices that are used there. All right, I'll kind of wrap things up. So we've talked a little bit about some of the basic transformations. So if you are looking ahead at some of the other ones, towards chapter 4, don't necessarily have to get there just yet. We'll start fresh there on Tuesday. What I'd like you to do with regards to the weekend and things is to kind of think about what you've done in the chapter 1 stuff so far, chapter 1 and 2, and sort of the basic pieces. Now, if you wanted to, it's really just a matter of kind of playing around with, now's the time to just sort of tinker. What would happen, for example, if you go back to one of the homeworks and you have, the simple idea where in chapter 5 you had this array here. You said draw arrays, and we passed it 3. Now, if we were to pass this 6, for example, we know then that the shader here, our weird vertex shader, would wind up getting called more times, right? 1, 2, 0, 1, 2. What would happen if you had it 3, 4, 5 and give it some other geometry? Right, that's the sort of thing you could do for this first project. Really just sort of experiment with what you have so far. If you want to go so far as to actually look a little bit ahead and get into the vertex array attributes done right, feel free to do that as well. Did everyone sign up? Hopefully, was everyone able to sign up? I see some. Looks pretty good, but not quite everybody. All right. I'll start contacting people, and we'll start using the sheet next week. Have a great weekend. Stay out of trouble. And by trouble, I just mean don't get COVID. Give a shout. I'll be at Discord all the time. Thank you so much. Don't, I don't know. Give me a shout if you need anything. Sound good? Or am I like way ahead and I have another hour?
Thank you for the lecture, Professor.
Hopefully, it's early on. It's kind of crazy. I know.
I was actually wondering how things were on like your end, like as the teacher, like with all the online stuff. I'm sure it's like wild.
It's challenging. Definitely there's been a few instances where people just suddenly like, oh, by the way, I didn't I haven't watched any lectures or done anything so far, and I need to add your class now. And I'm like, oh boy, how do we get people up to speed and quickly? And it's challenging. I'm unfortunately I'm kind of just stuck here. I haven't set foot on campus since a week before, maybe 2 weeks before the end of the semester. So I'm eager to find out how it's going on or what things look like out there.
Yeah, that's probably the smart way to do it. Yeah. Keep out of contact as much as possible.
Yeah, it's scary, I guess. Anyway, let me stop.